Hello from Ireland. I would like to thank the organizers of the conference for giving me the opportunity to talk today about our developments towards correlative cryo-light and soft X-ray tomography. And just before I continue, if somebody wonders, this is rock castle that is 900 years old. Sirius XT is developing lab-based tabletop X-ray microscope for imaging of whole hydrated cells in near-native state. So this is the image of our soft X-ray microscope. But before the cells get to this stage, they have to be prepared. So let's see how does our workflow look like. So first we grow the cells on the EM grids. When the cell culture is ready, we do plunge freezing in liquid ethane. And starting from this point, the grids have to be kept in cryogenic conditions all the time. However, before the soft X-ray microscopy, the cells have to be optically examined by optical microscope. And why is that? So there are several reasons for that. So first, we have to find the good cell candidates on the grids. The second reason is correlative light and soft X-ray imaging. And the last reason is to inspect the eyes quality of our samples. So let's say the first reason. So ideal cell candidate would be far from the grids and it would be a single cell. So these three cells, they're growing together, close to each other, they're not good candidates. Or these two cells, they're very close to grid bars. So the good cell would be far from bars and also it would be individual cell. So let's talk about correlative light soft X-ray imaging. So light microscopy does not have a possibility to image very fine cellular details. And for that reason, we use molecular biology techniques to label particular protein species, and that's how we can localize these species within certain organelles. However, light microscopy, fluorescence or not, it doesn't have very good resolution. So most of the cellular organelles or compartments are not clearly seen in light microscopy. So for that, if we need better resolution, then we use soft X-ray microscopy or electron microscopy, of course. And soft X-ray microscopy is great because it gives the view of whole cell in 3 dimensions at resolutions that facilitate visualization of almost all organelles and compartments. And if you want to know, to get information about protein species, then we have to combine soft X-ray imaging with fluorescence. And so the fluorescence, of course, we get from the light microscopy. So cells, once, as I said previously, cells, once they're plunge frozen, they have to be kept under cryogenic conditions all the time. So this fluorescent microscopy has also to be done in cryo conditions under 140 Celsius. So for this purpose, we built the cryo stage for inverted Nikon microscope. So this is the microscope that we're using. It's located at the University College in Dublin. And we use 100x air objective, working distance 1 millimeter and NA of 0.9. This is the model of our cryo stage. So for the inverted microscope, of course, the objective is under the stage. So we feed our sample through the top. This is the grid here. And finally, we operate at 80 Kelvin temperature. So we have a top white light for transmitted white light imaging. So we keep 80 Kelvin temperature within the cryo chamber by feeding liquid nitrogen periodically. So once again, we have top light, white light, and we also have several laser lines for the epifluorescent imaging. I also mentioned that we have to inspect the eyes quality. So let's demonstrate this. In this experiment, I took baker's yeast, that's just bread yeast. I labeled the nucleus with nuclei with host dye and deposited them on the grids and plunge freeze them. So these are the cryo images that we obtained. So black and white we got from the transmitted light imaging, and then pink nuclei are, of course, from the host excited with 4 or 5 nanometer laser line. However, we see contamination, plenty of contamination here. This big blob is larger than 10 microns. And we also see white bead-like structures that are probably under 1 micron in size. So the question is, where is this contamination coming from? So to answer this question, so this is the experiment that I've done. I dipped a clean grid into the liquid nitrogen and then loaded that kind of grid to the cryo stage. So a lot of black blobs were observed. So this contamination, if I can say, comes from the impure liquid nitrogen. And in the second experiment, a clean grid that was cooled in the cryo stage, I took it out from the stage for 1 second and just exposed to the air and then put it back in the stage. So this is the image that was obtained. So basically there is a lot of white bead-like structures, and this kind of contamination comes from the exposure to the air. So how to avoid, so finally how to avoid contamination. So if it's possible, it's best to avoid contact of grids with liquid nitrogen. And of course, it's never a good idea to expose the grids to the air. Just to give a comment on contamination in our cryo stage. We don't have contamination in our cryo stage, and this is the experiment to confirm this. So a cool grid, so the grid was, a clean grid was loaded on the stage at the room temperature, and then this grid is cooled to cryogenic temperatures. And it was observed for 2 hours. Within these 2 hours, there was no contamination of any kind on the grid. So no ice contamination occurs during cryo-light microscopy, so at even longer times, but we just have data for 2 hours. I would like to give a comment on mechanical stability of our cryo stage. In this experiment, 200 nanometer fiducial markers or beads were deposited on EM grid, and they were observed under cryogenic conditions. So if we focus a particular bead, we get this. So if you plot the intensity profile, so this is the function that we get. We can fit a nice Gaussian. So what we see from here, that the signal to noise ratio is really good, and also because of that we can easily determine the central position. This is the central position of the bead. So we can use the central position to track and evaluate the mechanical stability of the grid, but just tracking the central position of the bead in time. So we just record the video and then track the bead in time. So in this experiment, we tracked several beads. Each color corresponds to 1 bead. So this is the X coordinate of the center or Y coordinate of the center in time. So all the beads stayed very close to their position at the time equals 0. Or the other way so this is the drift in nanometers per second, 0.06 nanometers per second. Y was even better. So the other way, and maybe a clearer image we can get, if we plot Y coordinate versus I coordinate of the center of the bead for each frame that we took. So basically, this bead stayed within 5 nanometers relative to its first position. So we can determine the center, the position, or the position of this bead with very high precision of 3 nanometers. So precision or localization precision of the fiducial markers is very important for correlative imaging, because these fiducial markers are actually compared between modalities like light microscopy or soft X-ray microscopy. So we can localize 200 nanometer beads with very high accuracy and precision. And to conclude, we can conduct cryo-light microscopy for several hours without any kind of ice contamination. And also mechanical stability of our system can facilitate correlative imaging with very high precision. But not only that, the high stability of the system and also high signal to noise ratio can also be used for subdiffraction imaging and super resolution. And finally, the punchline. So we developed stable and artifact-free procedures for sample preparation, labeling, handling, and storage, and visual inspection of cryofixed cells prior to soft X-ray imaging. At this point, I would like to thank everybody for your attention.